Okay, good morning everyone. Let's start today's session. Uh, Today we are going to continue our discussion about what we learned in the class so far, and we are going to solve some example for both Bode plots and Nyquist, and get familiar with those kind of like type of problems and questions that you might face in the final exam. Now, if you don't have any question about the previous session or generally, I can start the examples. Do you have any question? No? Okay, let's start then today's discussion. Now, we are gonna start with the Bode plot example. The transfer function that I want to have as for the Bode plot is 1 over s plus 2. Oh, sorry, 2s plus 1. Okay, now, what we discussed about how to draw the Bode plot was first thing that we knew we have to do, the first step, because Bode plot is a frequency response, we need to change the s to the j omega. So we are gonna move it to a simple frequency without any real value for the s. So basically the first step is to write the transfer function when s is equal to j omega. So it's going to be 2j omega plus 1. Now, next step for such an example is to make the transfer function in a standard way. What I mean is to eliminate whatever coefficients this omega has. So we are gonna write it as j omega plus 1 over 2. Are we good? So this is the same. Divided by 2, this one should also divided by 2. Yes. The denominator is also 1 over 2. Now, based
not one over 2, right?
Sorry?
It's only 2 multiplication.
What do you mean? Which one? Denominator or denominator?
No, the upper one, the numerator.
I just divide denominator and denominator by 2.
Oh,
Okay, so I would have the standard version. Are we good? Yeah, okay. Now, we know that what we have to do for the Bode plot is to divide the value of the omega based on whatever constant number we have when we facing the constant number over s plus a. We already talked about how we can do that. So basically, the behavior of the frequency would be divided. We wanted to use the asymptotic lines. We wanted to divide it to before 1 over 2 and after 1 over 2. Okay, so we are going to have some omegas that are smaller than 1 over 2 and some omegas that are bigger than 1 over 2. Okay, now we wanted to see what's going to happen in our situation. What we have to do, we have two types of Bode plot. One was for the magnitude, okay, of the vector that represent our j omega, and another one was for the phase of that. So we wanted to see the behavior of the both magnitude and phase for the vector that represent our transfer function. So basically, this is going to be some vector with an amplitude and phase. When we know that the phase is simply the amplitude of what we have here, the denominator is simply a constant number, so it's going to stay the same. And the denominator, you have a complex number, which you know the amplitude is going to be the square root of the complex value square plus the real value square. Are we good? So, any question? No. Okay. And the phase is simply going to be based on that tangent relation between the real part and imaginary part, the denominator that we have is constant number, so the phase is going to be 0. Okay, so, and we know when we have a division for the complex number, the phase of overall situation is the phase of the denominator minus the phase of the denominator. So we have 0 at denominator minus, we have one complex number here, so we are going to use a tangent inverse to calculate the phase of this complex number, which is going to be the tangent inverse of the complex value omega over the constant value, which is omega over 1 over 2, which is 2 omega. Are we good?
Explain it again.
Which one? The tangent one?
The whole.
We wanted to like represent our transfer function with a vector. That vector would have a magnitude and a phase. Okay? The magnitude is simply the absolute value, the magnitude of this transfer function. Okay? Which we have a numerator and denominator. The magnitude of the whole system is the magnitude of the numerator divided by the magnitude of denominator. Now, this one is constant number, so it's going to be the same. This one is a complex number. The amplitude of a complex number is the square root of x squared plus r squared. Are we good? So, we are going to have a square root of omega squared plus 1 over half squared. Sorry, 1 over 2 squared. Okay? Now, for the phase, again, we have a numerator and denominator. Considering both as a complex number, the phase of the overall system is the phase of the denominator minus the phase of the denominator. Now, the denominator is a constant number, so the phase is going to be 0. For the denominator, you have a complex number, and you know the tangent relation between the real part and imaginary part. Okay? So, the phase of this complex number is going to be tangent inverse of the imaginary part divided by the real part. Okay, so what's happening is that? So it's omega over 1 over 2, which is 2 omega. Okay, now let's go back to the situation that we have. If omega is way less than or like less than 1 over 2, okay, for the magnitude, what's going to happen is that this 1 over 2 squared would dominate this square root. So we can ignore the omega. Remember, asymptote lines are basically approximation. Okay, so I know if it's like 0.001, we still have a number here, but we are using approximation, so we can neglect that. So if this is going to happen, like this is the dominating part, and we can ignore this one, this become 1 over 2 square root of a square, and then a square root, which is 1 over 2. Okay, and basically we have both of the numerator and denominator 1 over 2, so it's going to be 1. So the magnitude, the absolute magnitude for omega before 1 over 2 is going to be 1. Okay, now we said we want to have that, we want to show that as a decibel value. Okay, so instead of just simply say m, okay, we want to show the magnitude as 20 log of that m, which is 1 in this case. Are we good? Now, 20 log of 1 is 0, because log of 1 is 0. So, if we are below 1 over 2, our magnitude Bode plot is going to be 0. What about the phase? If omega is less than, way less than 1 over 2, okay, we are going to have a very tiny number. But for the phase, we said we are going to consider that exact value, 1 over 2, in our omega, finding what is the exact value for that specific point, okay, which if you see that, if you put 1 over 2 as an omega, you are going to have 1 here, Are we good? Okay, so what we are gonna have here is gonna be tangent inverse of, no, it's 1, tangent inverse of 1 is 45 degree. Okay, so that means in for the phase in omega equal to 1 over 2, the phase is gonna be 45 degree. Now, what's gonna happen in omega? In omega,
It's minus 45 degree.
minus, yeah, thank you. Minus, this is a minus here, thank you. If omega is very small, very close to 0, don't consider it as 0, it's very close to 0, then this is gonna be tangent inverse of 0, which is 0, right? So way before that 120, if omega goes to 0, our phi is gonna be 0. Are we good? Now, if omega goes, for example, to a large number, I want to say infinity, but it's not actually infinity because tangent is repeating itself. Okay, so even 90, even like the omega equal to phi equal to 90 would basically create that tangent equal to infinity. Okay, so if that's the case, then what's going to happen is going to be tangent inverse of infinity, which is minus 90. So at that phi we have minus 90 degree. So now we know what the phi would react. Now, the amplitude for omegas above 1 over 2 is the only thing that we are right now missing. We wanted to like have the asymptote lines for after 1 over 2. If omega is bigger than 1 over 2, again for the amplitude, now this omega square dominate the formula underneath the square root. So we ignore that part. We have omega square, and the square root would be basically equal to omega. Okay, and we have 1 over 2 divided by omega, which is 1 over 2 omega. Okay, so on that we are going to have 20 log of 1 over 2 omega. Okay, are we good? Now, if we have 1 over 2 omega, how we can bring that 1 over 2 part outside of the log? What's going to happen to that? We can simply divide these two, okay? And the log of 1 over 2 omega is going to be the log of 1 over 2 times the log of 1 over omega. Are we good? The log of 1 over 2 is a constant number. Let's say a. Okay, so this one is actually become 20 log of 1 over 2, okay, plus okay, we are missing something, okay, so this is 0 minus, this was 0 minus, because the denominators also have to be considered, 0 minus 20 log. It is 0, so it doesn't change anything, but this one is also 0 minus 20 log of 1 over 2 omega, which is basically minus 20 log of 1 over 2 times times log of 1 over omega. Are you clear what's happening here? Are we good on that? Now, this part, oh, sorry. Yeah, sorry. This is 0, this is gonna be 2 omega, so it's gonna be 2 omega. That denominator is 20 log of that value. Let me do that again. I made a little bit of error. So if omega is bigger than 1 over 2, we ignore that 1 over 2 squared. We have 1 over 2 divided by omega. Okay, so it is going to be 20 log of 1 over 2 omega. Now this one, we can split the numerator and denominator. It is going to be 20 log of 1, which is 0, minus 20 log of 2 omega. Now, you can extract the 2 out of that, so it's going to be simply 20 log of 2 times 20 log of omega. Are we good? So we can extract that, but you don't need to do that actually, because eventually we are going to see a line with a slope of minus 20. Is that clear what we're talking about?
So in that case, no need to subtract from 0, like 0 minus 20.
0 minus 20 log of 2 omega. We just use the characteristic of the log to split the numerator and denominator.
So no need to consider the numerator in that case.
Sorry?
No need to consider the numerator in that case.
The denominator,
Yeah.
because it's a constant number, is 0.
Okay.
But it changes the polarity of the rest. Okay? So, let's draw what we have for our Bode plot. Now, we said this is the point 1 over 2. We said before 1 over 2, we have a 0. Okay? So before 1 over 2, our asymptote line is 0. And after that, we have a line with a slope. If I have this decreasing line with a slope of minus 20 dB per decade. Okay? So we are going to see a decreasing line, and the slope of that line, based on this value, is minus 20 dB per decade. Is that clear? Any question about that?
Can you please explain the half? This part, yeah.
This part?
No, the first part.
This part?
Yeah.
This is the omega below 1 over 2. The magnitude is 0. So it's on the zero line until we reach 1 over 2, and then we are going to have this decreasing line, which is the slope is basically whatever coefficients we have before log. Here is minus 20, so it has a slope of minus 20 dB per decade. Are we good? Now, let's go for the phase. That was for magnitude only. For the phase, and this is 1 over 2, let me use another color. This point is 1 over 2. Now, this is 0. The numbers that we have is 0, minus 45, and minus 90. Okay? Now, we said when we wanted to show this phase, okay, what we need to do in the graph is for this 1 over 2, we need to consider another 2 points. One is a decade before 1 over 2. This is basically 0.5, so we are going to have 0.05 here. Let me actually, this is 1 over 2, and this is going to be 1 decade before that, and then 1 decade after that, which is 5. Is that clear? Now, for omega goes to 0, okay, we are going to consider a constant line from 0 to 1 decade before 1 over 20, 1 over 2. So the whole, this part from 0 to 1 decade before our actual cutoff, we consider it as omega goes to 0. So this is going to be 0, so here we have a 0 value. For omega goes to infinity, we are going to consider that omegas that are after a decade above our main cutoff. So after 5, we are going to consider omega as very big, as I mentioned, goes to infinity. And then after this part, we are going to have that minus 90 line.
0.05 and 5 is just random values.
No, 10 times lower than our cutoff, 10 times higher than our cutoff. So this is 1 over 2, then we are going to go 1 over 20, okay, and 10 over 2. Make sense? Now, we know that omega equal to 1 over 2 is minus 45. So at this specific point, we are here. Now, the change between the decade before and the decade after, we consider it as a line. As we said, we are going to use asymptotic lines, which are the approximation of the behavior. So it is going to be start here, has the value on the cutoff, which is here is 1 over 2, and then reaches the other asymptote at the decade after the cutoff. Now, you can imagine, and it is obvious that this line, the slope is 45 minus 45 per decade. Are we good? So that way, we basically draw the Bode plot for this specific function. Are we good? Is there any question? No? Okay. I wanted to erase that. I wanted to move to the next example. Are we good? For next example, we are going to try to actually draw the Bode plot for a more complex situation, like a second order situation. Now, remember, when we have more complex transfer function, okay, we can split that higher order transfer function to a bunch of first order and second order term, and eventually the general Bode plot is going to be the summation of all the Bode plots for those terms. Do you remember that discussion that we have? So whatever transfer function that we have, we can simply split it to the first order and second order transfer function, and then use the characteristics of the decibel and log, and basically the result is going to be the summation of all those individual Bode plots. Now, next example that we have is g of s equal to 4 over s squared plus s plus 4. You good? Now, again, the first step is to put j omega instead of the s. So our g of j omega is going to be 4 over j omega squared plus j omega plus 4. Are we good? Now, we want to represent it as a vector, so we need to find the function that describes the amplitude and the phase of this transfer function. Now, for this one, the amplitude is going to be the amplitude of the numerator over the amplitude of the denominator. The denominator is a constant number, so it's going to be 4. Okay, this one is basically minus omega squared. You know that. Okay, so what's going to happen is that we are going to have omega squared. The amplitude is going to be the square root of omega squared minus a plus 4 minus omega squared squared. Is that clear? This is the amplitude of this one. This is minus omega squared, so basically the real part is 4 minus omega squared, and the imaginary part is omega, so this is going to be the amplitude. Are we good? Very good. Now, we said the split in a second order situation is the natural frequency of that second order system. Now, looking at this second order function, you can imagine, and you know basically by the standard situation of the second order was the coefficients of a square should be 1. Okay, that was the standard representation of the second order system. And if we have that, whatever constant number we have is going to be omega n squared. So by the look of this transfer function, we know that the omega n for the denominator, the omega n basically for the system, is going to be a square root of 4, which is 2. Because the cutoff for our second order is going to be omega n. Are we good on that? Now, the phase value, the phase function for this transfer function is going to be the phase of the denominator, which is a constant number, so it's 0, minus the phase of the denominator, which is 4 minus omega squared plus j omega, okay, which is minus tangent inverse of that complex number, which is omega over 4 minus omega squared. And then we have our phase formula for that vector. Is that clear what we talked? Any questions so far? No? Now, we said the cutoff for the second order is omega n. So we are going to see the situation when omega is less than omega n and omega is bigger than omega n. And we want to show and find what are the asymptote lines that describes that part. Okay, so let's try it. The amplitude wise, if omega is less than omega n, okay, which is basically less than 2, this is 2, and this is also 2, we already calculate that. If omega n is way less than 2, this one becomes 4, or basically 4 squared. Are we good? And again, we can neglect this one also. Okay, so the whole denominator would reduce to the square root of 4 squared, which is 4. Are we good? And the denominator is also 4, so it's going to be 4 over 4, so it's going to be 1. And then we are going to have the 20 log of 4 divided by the 20 log of 4, which is going to be 0. Sorry, subtracted by 20 log of 4, which is going to be, the amplitude is going to be 0. Is that clear what happened? Are we good? Now, what about the amplitude when omega is bigger than 2? If omega is bigger than 2, we can ignore the 4. Are we good? We can ignore the 4, and then what we are going to have is minus omega square, all again a square, which is going to be omega to the power of 4, and then we are going to have omega to the power of 2, which basically means that amplitude, that m, is going to be 4 over omega times, I kind of like factor 1 omega square and bring it outside of the square root. 1 plus omega square. This is the same as the amplitude when we neglect the 4 in the denominator. Are we good? Now, if that's the case, what would be the amplitude, the actual amplitude in decibel? Let me do that. This is 1, then the decibel wise is going to be 0. And now the decibel wise of our m for omega bigger than cutoff frequency, or omega n, is going to be denominator, which is 0. Oh, sorry, which is 20 log of 4. Are we good? The 20 log of denominator minus the 20 log of omega square root of 1 plus omega square. Any question?
Well, I'm still kind of confused how you went from the transfer function or the J omega to the square root in the denominator.
This is our transfer function. We wanted to represent it with a vector. That vector has an amplitude and a phase. The amplitude of this transfer function, okay, this transfer function that we have is eventually that g of j omega is eventually 4 over 4 minus omega square plus j omega. This is our transfer function. I just put the constant number, which is omega square minus omega square and 4, together as a real part, and then we have imaginary part of j omega in the denominator. Okay, now the amplitude of this one is simply the amplitude of the denominator, which is 4, divided by the amplitude of the denominator, which is a complex number, and we know how to, calculate that. So this is what happened over here, and you know how to also do the phase function based on omega. Now, this is a constant number. We are going to keep it in mind. But this one, okay, is going to be our slope line, which is minus 20 log of omega. Are we okay for that? Any question on that?
Can you just repeat what you said?
Sorry?
Can you just repeat the line what you said?
This one? This is our absolute value when omega is bigger than 2. We neglect this 4. We eliminate that 4, and this is going to be the value. Now, in dB, in decibel, it's 20 log of nominator minus 20 log of denominator. So that's where this came from.
What you said about the slope?
Whatever, this is a function of omega, okay? Then whatever value that we have as a coefficients here is going to be the slope of our ascending line. Are we good? Now, for the phase, if we have we have omega way less than 2, okay, way less than 2, then these two are neglected, right? We have 4 over 4, which is a constant number. So for omegas less than 2, our phi is 0. Are we good? For omegas way above 2, we are eliminating this 4, okay? So it's become tangent inverse of omega over minus omega over omega squared, which is minus 1 over omega, and omega goes to infinity. So this one is become the tangent inverse of 0. Does that make sense? We neglect this one because omega is way bigger than 2. Are we good? So we have omega over omega squared, and we have a minus sign here. So we can cancel out denominator, 1 omega from denominator and denominator. So we are going to end up in minus 1 over omega. And we say omega is going to infinity. So it's 1 over infinity, which is 0. Okay? And what is the value? What is the tangent inverse of 0? 0, right? So again, phi at omega above I am missing something. There should be a minus 180 somewhere. Minus 1 over omega. I think I'm missing something. 0. Is omega, if omega is way bigger than that, it is going to be j omega minus omega squared, which is minus j omega over 1 which is, yeah, okay. Let's look at this part, okay? If omega goes way bigger than omega n, this is not a real factor, okay? So this denominator basically become minus omega squared plus j omega, okay? Which is basically, we can swap the minus part and say it's omega squared minus j omega. Are we good? Are we good on that? So this is the phase of this one is omega times omega minus j. No, I'm not missing something. So this is actually accurate. So this is phi equal to 0. Now what happens in omega equal to omega n? If omega is equal to omega n, which is 2, this becomes 2, this becomes 4, this becomes 0. So it's become minus tangent inverse of infinity, which is 90. So if omega is equal to 2, then we have minus 90 degrees. Are we good? Now, if we draw the asymptote, if we draw the Bode plot, this is our omega n, which is 2, and for the phase also. Now, for omega n, for the magnitude, below omega n we have 0, so this is what we have here. Let me use another color. We have here. Are we good? For after omega n, we have a slope line minus 20. So we are gonna see plus that 20 log of 4, which is a very small number here. So we are gonna see such a slope. Now, we can have discontinuity. That means the actual behavior is a very small increase in omega n and then a slope to infinity. Is that clear what happened? Now, for the phase, again, we need to consider 1 decade before and after the cutoff. So we are here at 0.2 and 20. For way less than omega n, we have 0. So before 0.2, we have 0. For omega n itself, we have minus 90. Let's say this is minus 90. And for after 20, which is the bigger omegas, again we have a 0. So what's going to happen? We are going to end up in a decrease. You can consider the asymptote line with two slope, okay, which is 90 degree, minus 90 degree in the 0.2 to 2, and plus 90 degree per decade from 2 to 20, okay, and then we have our phase values. Any question? No? Are we good? No, I wanted to move on to the Nyquist example, if you don't have any question. Okay. For the Nyquist, the example that we want to talk about is the transfer function g of s h of s equal to the k s times s squared plus 2s plus 2, okay, and that's what we are going to have in our transfer function. Are we good? Is that okay? Are we good? Now, first step, was to find the gj omega, actually basically put j omega over instead of s, and then our transfer function become k over j omega times j omega squared plus 2j omega plus 2. Now, what was the first step that we have in our Nyquist? To develop our S domain. Very good. So for S domain, we have to put the poles of our system. We have one pole at origin, okay? And this one, if you solve it, it is going to be a conjugate complex number of -1 plus j and minus j. So we are going to have, this is 1, 1, minus 1, 1. So it is going to be 1 here and 1 here. G minus j and minus 1. Now, for stability analysis based on the Nyquist, we needed 3 numbers. One was the poles on the right hand side, another one was the zeros on the right hand side, and then how many net clockwise rotation we are going to end up in our function domain, in our mapped Nyquist, around point -1. Are you good? So, before we consider how many poles we have in our S domain, in the right hand side, we have to see, because we have a pole in the origin cutting the j omega, we have to turn around that pole either from the right hand side or in the left hand side. You remember that discussion that we have? So we know that we are going to have a contour that goes to infinity, but near that pole either we can turn around here or here. We are going to consider it in our example that we turn around on the right hand side. Are we good? So this is going to be point A, point B, C, D, E, and F. Now, since we consider the contour to the right of this pole, we don't consider this pole as a right hand side pole. Are we good? If we would go over other ways around, then we would have one pole to the right of our contour. Is that clear what I'm talking about?
Just repeat it.
Our contour, all the contour is to the right of all the poles. So we don't have any poles or zeros on the right of our contour. Okay? If we would have turned around on the left hand side, then this pole would fall to the right of our contour. So we are going to have one pole on that case in the right. In this case, we don't have any poles or zeros to the right of our S domain. So our pole is going to be 0. Poles in the right hand side is going to be 0. And we don't have actually any zeros, so this one is going to be also 0. Okay? And now we need to map the contour into our mapped domain, which we can call it T or F, that doesn't matter. Is the function, the transfer function of the overall feedback. Okay? Here, I'm going to define the overall feedback, which is 1 over K over, is that? No. Kg over 1 plus KGH. So I'm going to use T. So this one become T domain. and this is estimate. Now I'm going to start mapping. For the mapping, we said we are going to use those specific points to find where these specific point A, B, C, D, E, F would fall in our mapped domain. So, for the first one, we need to calculate the magnitude and phase of A prime, which is the mapped point of A. In order to do that, we need to have the function for magnitude and phase for our actual j omega transfer function. So, based on this one, the magnitude function, let me do that. The magnitude of GH is going to be denominator divided by, if you do that, is going to be omega times 2 omega square plus 2 minus omega square. Are we good? This is simply the magnitude of this second order, and this one is the magnitude of this outside term. Good? For the phase, of this GH, we are going to have 0 minus, this is j omega, so it's going to be minus 90, okay? It's going to be 90 degree, okay? And this one, the phase of this one is going to be tangent inverse of the imaginary part, which is that 2 omega divided by the real part, which is 2 minus omega square. Are we good? Now let's actually find what happens to the A prime and sorry, to the A prime and B prime and all the points. Now, A prime, A is basically, because we consider this radius lowercase r goes to 0, and this radius capital R goes to infinity. Since A happened to be at 0 or our origin, based on our assumption, okay, then that means omega goes to 0. If omega goes to 0, this one becomes 2, this one becomes 0, so it's going to be a square root of 2 squared, which is 2. This one becomes 0, so it's going to be k over 0, right?
Why omega is equals to 0?
A is on origin. The omega for A is 0. Okay? We put for the A prime, we need to consider omega equal to 0, or omega goes to 0, either way is work. Okay? If that's happening, the value, the magnitude is simply going to be, this is going to be 2 omega, this is going to be k. If omega is 0, it's going to be k over 0. So m goes, the magnitude goes to infinity. How about the phase? If this is 0 and this is 0, this one becomes tangent inverse of 0, which is 0. So this one becomes minus 90. Are we good? So the phase of A prime become minus 90. So where is that? Infinity and minus 90 is going to happen somewhere here. Are we good? It's on infinity with a degree minus 9. Let me actually like draw it in the axis so there's no confusion. What about B? The omega for B is infinity, correct? So if omega is infinity, this one become omega squared plus omega to the power of 4, okay, times omega. If omega goes to infinity, this whole thing gonna go to infinity, so it's gonna be 4 over infinity, which is 0. So for B prime, where omega goes to infinity, the magnitude of B prime is gonna be 0. What about the phase?
Minus 180.
The phase of B prime is 90. Okay? So, but we can either work with that or use the omega infinity. This is 2 omega, this is gonna be minus omega squared, which is minus 2 over omega, which is infinity. So this one become 90, so it's gonna be 90
Plus 90.
plus 90 minus 180. Are we good? No, it's 2 omega. 2 over omega. Omega goes to infinity. It's become, right? Omega goes to infinity. It's going to be minus 2 over omega, which is 0. So this one becomes 0. Are we good? So this one becomes also minus 9. Are we good? Yeah, so this one also becomes minus 9. So it's going to be on 0. But remember this, we are going to leave that later on, because this is the angle that we move toward that phase.
Why B prime is at horizon?
The magnitude is 0.
Oh, okay.
Yeah. Now, for the let's do the B prime, because it's gonna change a little bit. I'm gonna try to eliminate that. This is not, I don't think this is correct. It's kind of like, I have problem with that. Okay, so let's stick to that and try to use that formula that we have when capital R goes to infinity. Okay, so when R goes to infinity, meaning the curve BCD, okay, the way we are gonna deal with that is to consider the limit of our GH, okay, GH, when S is capital R EJ theta, when R goes to infinity. Okay, so if we have that, then our function become limit of here K over this one become R e to the power of j theta, okay, and the second order one become R squared e to the power of j 2 theta. This is the first one, the first S squared, plus 2R e to the power of j theta, plus that 2. Are we good? I put R equal to R e to the power of j theta instead of S. And we limit the R to infinity. It's capital R. Now, if that's the case, okay, and R goes to infinity, we don't have this one, we neglect this one.
Can you please tell me like what you did there?
we want to consider the point B, C, D in infinity. Okay, so instead of considering a value of infinity for that, okay, we simply gonna limit the S to the R ej omega, ej theta when R is infinity. Okay, instead of exact value for the function, we limit that. Okay, now, if R goes to infinity, this one is absolute. Okay, this one compared to this R square is also negligible. So we are gonna have R square times R. So this one become limit of K over R cube J, so e to the power of J 3 theta when R goes to infinity. Now, we want to have B prime, C prime, and D prime. So B prime, C prime, and D prime. If R goes to infinity, the amplitude of all of them is going to be 0. Are we good? Because we have infinity in the denominator for all three, and a constant number in the denominator. Is that clear? For C, D, and B, R goes to infinity. If R goes to infinity, this is constant number, this is the amplitude is R cube, sorry. So it's gonna be K over infinity. So all the amplitude is gonna be 0. So MC prime and MD prime are also gonna be 0. We already know that before we calculate that, but from this formula we can also confirm.
Can you please tell me how you find R cube?
Here, if R goes to infinity, this 2 is negligible. Now, the R compared to R squared when R goes to infinity also can be neglected. So we have R squared times R. Okay, so we have R cubed. And this e to the power of J2 theta, and J theta is going to be 3 theta. Okay, so this is the case. Now, how about the phase? The phase of the C prime, B prime, and D prime. Now, the phase is going to be 0, okay, minus whatever phase we have in the denominator. So for B prime, we have 90, okay, so 3 times 90 is going to be 270, and we have 0 minus 270, so here we have minus 270 degrees. Are we good? I put the theta of B in this formula. So here the theta is going to be 3 times 90, which is 270, okay? And we have the whole situation become 0 minus 270, okay? So it's going to be minus 270. Are we clear? For B prime, we need to put the values for B. We know R is infinity already, okay? The theta of B is plus 90. Are we good? So if we put plus 90 here, the theta of the denominator become 270. 3 times 90. Okay? And the theta of the denominator is 0, so the whole thing is become 0 minus 270. So we have minus 270. Okay? For C, we know the amplitude. The phase of the C is 0. Are we good? So this is also going to be 0, and 0 minus 0 is 0. Any question? C, the theta of C is 0. We put 0 at theta. 3 times 0 is 0, so the phase of the denominator is 0, so as the phase of the denominator, so eventually all the phase becomes 0. The overall phase. For D, the phase is minus 90, okay? The phase is minus 90, so if we put minus 90, we have minus 270 in the denominator, the overall thing becomes 0 minus 270, which is 270. Okay, we need these numbers later on. So all three B prime, C prime, and D prime happen to be at the origin. Okay, but different phase angles. Now, I said we need those phase angles, and the fact for what we need is when we wanted to actually see how the trajectory would end up to those numbers or came out of those points. Now, our trajectory is, I should have drawn that, from A to B. So the map trajectory also is going to be from A prime to B prime. The A prime has a minus 90 degree, so the trajectory is going to be like this, okay, minus 90 degree. And for B prime, we have minus 270, which is going to be this, okay. So we know that this would leave like this, and this would leave like this. Now, there is another point. We don't know how they would reach out. We know that this is going to be going up and then down, okay? But at what point it would go down? We need to find when this trajectory would cross the real axis, which is omega equal to 0. Are we good? Now, if omega is 0, what we can do is to find the value for phi. For phi, for that number, whatever number is here that crosses the real axis, we call it m, okay? The phi, the phase is going to be 180 or minus 180. Let's call minus 180 is easier to calculate because we have a minus sign over there. Okay, if it's minus 180, that means this should be 90. If this one equals to minus 180, this is minus 90, this should be also minus 90, so you would end up to minus 180. Are we good? So, if the tangent inverse at the point M, if the phase of point M is minus 90, that means that tangent inverse should be equal to infinity, or goes to infinity. That's a better statement. Are we good? So if that goes to infinity, the function is 2 over 2 minus omega squared. If the tangent inverse goes to infinity, this one should, the tangent should go to the infinity. That means 2 over 2 minus omega should go to infinity. Are we clear? The tangent of the phase of M should go to infinity. That means the 2 over 2 omega should go to infinity. When would that happen? When the denominator is 0. So that means 2 minus omega squared should be 0, which would happen only if omega is a square root of 2. Are we okay? Is that clear? Now, what would be the value of m if omega is the square root of 2? We put that into the amplitude function. the amplitude of m is gonna be that gh amplitude when omega is equal to the square root of 2, which if you put that, this one become 2 minus 2, this is 0. This one become 2 square root of 2, okay, which is 4 times 2, which is 8, okay, and this one become a square root of 2. You can bring that inside that, so it's become a square root of 16, okay, so which is 4. So eventually this one become k over 4. So here m, here is point minus k over 4. So we know now that we are crossing the real axis at this point. That means the trajectory is going to be going up and then cross the point and then come back to infinity. So it's actually the reverse. Goes from the infinity to that point and then come back to b prime with those angles that we find. Are we good? Any questions so far? No, I'm gonna erase this because I need the space. Now, what we are left so far, did so far is A, B, C, D. Now we need D to E and then E to F. Now, we said Nyquist is simply a symmetric kind of like contour. So if A to B is mapped like that, that means D to E should be the mirror of it. Are we good? Now you can use the E here, okay, let's actually do that. I don't want to like just give you a description. Let's go mathematically. For EFA, for that part, we know that again, we are gonna use the limit of G and H because this R goes to 0, not actually 0, okay? G of H of R, lowercase r, e to the power of j theta, okay, when R goes to 0, then if that's the case, the function that we have, the transfer function that we have for part of the contour for EFA is gonna be, this is gonna be, RE is gonna be limit of K over RE j theta times R square e to the power of j2 theta plus 2 R e to the power of j theta plus 2. Very good? And R goes to 0. If that's the case, if R goes to 0, what's going to happen here? These are zeros, so 2 will dominate, but we have a multiplication by R again, which is 0, so it's going to be 0, K over 0, all our amplitude become infinity. So for E prime and F prime, our amplitude become infinity. Now let's go for the phase. Eventually, as we said, this become the limit of K over 2R, 2 lowercase r, j theta when R goes to 0, okay? This is the overall function. We neglect this one. This is 2rg e to the power of j theta. Okay, if R goes to infinity, the amplitude is r goes to 0, the amplitude is infinity. But for the phase, we need to put the phases in. So E has a minus 90 degree.
Why you
Okay.
neglect this term?
R goes to infinity, R goes to 0. So this one is R squared, basically goes to 0. This one also, so it would only, we have 2. And then we don't want to like fully neglect that, so the function would be 2R E G theta, the J theta. The reason that I keep this one is because I need this theta. Okay? Now, if for E, the theta is minus 90, that means here in the denominator we have minus 90, so it's going to be 0 minus minus 90. So the phase of E prime is going to be 90 degree. Are we good? F is 0, so it's going to be 0. 0 minus 0 is 0. A prime, we already have it, is minus 90 degree. Are we good? So E prime is going to be infinity 90, so it's somewhere here. This is E prime. And F prime is infinity 0, so it's somewhere here.
Can you please tell me again how you find 90? E prime?
This one. E has a minus 90 degree. We put minus 90 degree into the formula. The phase of the denominator becomes minus 90. The whole thing becomes 0 minus minus 90.
Yeah.
Okay? So, we know the symmetry. So, from D prime to E prime, remember, we have 270. 270 for D prime, so D prime would leave with that angle, okay? And E prime we would reach the E prime with that angle, 90 degree. See, D prime is 270, this angle, and E prime is 90, this angle. And we know the symmetry in a Nyquist, so this one should mirror the other part. Are we good? And then F is infinity with 0. When we're gonna go to the F, we are simply connecting the E to the F prime to the A prime. Are we good? Now, are we done, or we need something else? Because eventually we want to have a stability analysis. We can't actually find if we, this is like that. If we actually encirculate the point minus 1, because we don't have the absolute value of m, which if you remember, it was minus k over 4. We don't know if that is happening below minus 1, so we end up no encirclement, or above minus 9. Or like, so we have one clockwise encirclement. Is that clear what I'm talking about? The n was the net clockwise encirclement around minus 9. We don't know minus 9 would happen here or here. If minus 9 happened here, we don't have any encirclement. If happens here, we have one encirclement. Okay? So for what value of k we would have no encirclement? If here we have two situations. If k over 4 is bigger than 1, okay, that means k is bigger than 4, okay, what's going to happen? Minus 1 would end up inside that circle. So then n become 1 and system is unstable. Are we good?
How n is equals to 1?
If k over 4 is bigger than 1, that means minus 1 would happen inside this encirclement, right? Are we good? If k is bigger than 4, that means minus k over 4 happens here, and we have minus 1 here. So we have n equal to 1, and we know the formula for stability was z equal to p plus n. This formula, these two are 0. If this is 1, then our system is unstable. If k over 4 happen to be less than a 1, which means k is between 0 and 4, then n becomes 0, so we have an stable system. Are we good? Any question? Are you good on that? So this is how we can first plot the Nyquist, okay, and then find out for what condition we have the stable situation or an unstable situation, for what value of the k. Now, if you happen to not have a k and was constant number, then you don't need to consider this m as a function of the k. You already know if m is before minus 1 or after minus 1. You get what I'm saying? So this is how we do the stability analysis for using a Nyquist for our transfer function. Any question? No? If you don't have any question, this is for today. I'm sorry I passed the time, but have a great rest of the day.